Okay, in this video we've got a structural member here that's got a couple of loads on it, but the important piece here is that it's a combined loading example. Actually, I've got two videos here. One is, well, they're both combined loading examples, and they both have different looks to them, but in both cases we're going to have multiple types of loads that we have to add up in order to get the stress at a particular location. And in this case, we've got a load H here and a load P that are both going to be giving us normal stresses at these locations at the bottom corners, A, B, C, and D, and we need to keep track of what's going on at those locations in terms of normal stresses. Let's first add in what kind of loads we have. P is actually 9,600 pounds, and the H load right here is 800 pounds. £800. I don't know why it does that. That is really obnoxious. 800 pounds for that H. What I'm going to do is draw two free body diagrams here from two different directions. And the reason I'm going to do that is because even though it might not look obvious right now, there's actually a couple of bending moments in two different directions. So let's actually draw axes on this shape that follow or that come out of that origin right there. So I'm going to call this the x-axis, this is the y-axis, and this is the z. Right? So the first free body diagram I'm going to draw is going to be like this, such that we can see the H 800 pounds over here and the P 9,600 pounds axially. And the bottom of this thing is going to have some reaction P, and it's going to have some reaction My. All right. So that My is the moment about the y-axis. All right. So I don't know if that makes sense yet or not, but basically what I've just done is I've just drawn this face, and I'll outline it right here. I've just drawn this face of this thing. All right. Now, let's also, because this is going to be important later, let's also label the corners of this thing. This corner down here is A, and this corner down here is D. That's coming from the original A and D from that original drawing. But also notice that, you know, if I could look behind the A right there, on the back corner is B, and on the back corner here of the back corner behind C, sorry, the back corner behind D is corner C. All right. Another piece that's going to be important here is figuring out what that bending moment is, and that bending moment we can find by summing the moments about the y-axis. Right. So I'm going to have a plus my, and I'm going to have a minus 800 times 24 inches equals 0. So that's going to give me an my of 19,600 inch-pounds. All right, now an important piece here is to understand that at those different locations, those different corner locations, A, B, C, D, I'm going to get a contribution to normal stress from the axial load P, but I'm also going to get a contribution from a flexural stress from that bending moment My. All right. So, so what I'm going to do here is change some colors just to make it clear what we're doing. So let's say that I've got some sort of axial stress, and I'll call that sigma 1. Right? That's the axial stress from the that's the normal stress from the axial load. But then let's change colors to green here, and I'm going to get a flexural stress from that bending moment, right? And this flexural stress, hopefully this makes sense to you, but because of the direction of that moment, it's going to be compressive on this side and tensile on this side, all right? And we'll label that sigma 2. So basically we've got a sigma 1 and a sigma 2 contribution there from those two loads. So now let's draw this same structural member, but from the other direction, so that we can recognize, or I should say calculate, the influence of the fact that this load P right here is actually offset by 1 inch from the center. All right. So let's draw another diagram here. And in this case, I've got the load P, that 9,600 pounds here, and it's offset by 1 inch, like that. Whoops. It's offset by 1 inch, and that's going to give me a reaction down here at the bottom of P, but it's also going to give me a moment down here because of that offset. That moment is mx, all right? That's going to be about the x-axis. All right, so now what I've just drawn, is this face over here. All right, and I'll hatch it with a different direction here, but this face is what I just drew. All right, this face is what I just drew, and so the moment about the x-axis you can see coming out here along this axis, and if we label the corners, this corner right here is D, and this corner right here is C, and behind that corner, in the back corner, is A, and in the back corner back over here is B. All right, and once again, I'm going to have a normal stress from the axial load of sigma 1. That's still going to be the same as it was before, but now I also have a flexural stress. Now I'll make this one purple. I'll have a flexural stress now from this mx. All right, and like we had before, I've got a compressive stress on this side and a tensile stress on this side. All right, and that one I will call sigma 3. Now we haven't calculated the moment there. Let's actually calculate what that moment mx is. So if we sum moments about the axis, the x-axis, I'm going to have a mx, which is the one that's on the free body diagram there, and I'm also going to have a minus 9,600 pounds times 1 inch. That equals 0. So my mx is 9,600 inch-pounds. Okay, so the next step here is going to be to compute sigma 1, sigma 2, sigma 3. So let's do that on the next page here. Sigma 1 is an axial load. That's just going to be P divided by A. Our P is 9,600 pounds. The A is just 6 inches times 4 inches from the previous page. That's going to give me 400 psi. That's in compression, so I could have written that as negative 400. Sigma 2, I'm going to write this as sigma mx, and that's going to be the moment about the x-axis times c over I. And now I wrote that as a c because we actually have a positive and a negative component of this, so we'll deal with the positive and negative component in a minute. The I, in this case, we have to be careful about how we calculate that I. All right, so let's just make a diagram here of what that I is going to be. We've got 1/12 base times height cubed. All right, and if we're talking about this thing as bending around the x-axis, which is what bending around the. Oh, did I just write that wrong? Yeah, my sigma 2, whoops. Right, what I talked about as sigma 2 is bending about the y-axis. So, sorry about that. Let me correct that. Bending about the y-axis. So we're dealing with my. And if that's the case, then let's go back here and see what our dimensions are about the y-axis. So if we look here at the y-axis, all right, then you could say the depth, above and below the y-axis there is that 6 inches like that. So that means that when we calculate this, we're going to do something like this. This is the y-axis. This is 6 inches. This is 4 inches, which means my base is the 4 inches. The height is the 6 inches. So that means this is going to look like 1/12 4 inches times 6 inches cubed. All right, and then my C is going to be either up or down from the neutral axis there, which is the same as the y-axis in this case. All right, so let's put those numbers in. My my is 19,200 inch-pound. My C is 3 inches, and my I is this 1/12 base times height cubed, which is going to give me 800 psi. And that 800 psi could be in tension or compression, depending on which side of the axis I'm on. All right, so let's do the same thing for sigma 3. Sigma 3 now we'll call the sigma due to the moment about the x-axis. So we'll write the moment about the x-axis times c over I. And in this case, if I want to look at the axis there that we're bending around the x-axis, now we look here at the x-axis. The depth of this section above and below the x-axis is this 4 centimeters. So that means that if I draw this thing like this, the x-axis being here, this dimension is 4 inches. This dimension is 6 inches. All right, so that means that my base in this case is the 6 inches. So 1/12 base times height cubed is going to be that 6 inches as the base, and then the height is the 4 inches cubed. Right, and in this case, I think I called it the depth, above and below the x-axis. So a lot of times when we talk about, how a beam is being loaded, we talk about the depth in the direction of loading, and that's 4 inches in this case. So let's do these calculations with mx. My mx is 9,600 inch-pound. My C in this case is 2 inches. That comes from this dimension here. And my I is 1/12 6 inches times 4 inches cubed, which is going to give me 600 psi, and that's tension or compression again, which we'll have to figure that out from the orientation or from the locations of all the A, B, C, D. So now we've got sigma 1, sigma 2, sigma 3. Those correspond to the blue and the green and the purple that we have in this diagram. So let's look now at just one location. We'll just look at the A, the corner that we're calling A. If we look on the left figure over here, A has a compressive load from sigma 1. It's got a tensile load from sigma 2. And if we look over at the second diagram here, the A is behind, is behind the D, but it's on the same side of the member. So it's going to have a tensile load from sigma 3. So let's put that together and say in this diagram here, or in this page, we'll say the normal load at A is going to be, and I'll make it the same color. I'm going to have a compressive contribution from sigma 1. Let's go back. I've got a tensile contribution here from sigma 2. I'll make that green. So plus sigma 2. Now let's look at, again, just review again what sigma 3 had. So sigma 3 has, because it's on this side of the member, sigma 3 is also tensile for point A. So sigma 3 is also tensile, so that's also going to be plus. So purple plus sigma 3. All right, and if we write what those are, I'll just switch back to red here. That sigma 1 is negative 400. Sigma 2, let's look back at our previous page here. Sigma 2 is our 800 psi, and sigma 3 is our 600 psi. So we'll have plus 800 plus 600. That's all psi. If we sum those up, I'll get 1,000 psi. And since that's positive, that's going to be tensile. All right. So that's the stress at A, and that's the contribution from each of those three loads. All right. Or I should say, sigma 1 is an axial load. Sigma 2 and 3 are both moments, and they're both giving us flexural stresses. All right. So let's do the other corners. Sigma B then is going to have, for sure it's going to have this minus sigma 1 because all four corners have the same compressive load. Let's take a look at what 2 and 3 are going to do to point B. All right. So let's look at this left side over here. Point B, the corner of B, is behind A, so it's on this same side of the structure as A. So I'm going to have a tensile load from sigma 2. So that means that my tensile, or my sigma 2, is going to be plus sigma 2. Let's look at what B looks like for the purple load, sigma 3. In this case, it's on the same side as point C, and those are both compressive flexural stresses from sigma 3. So that's actually going to be a minus sigma 3. So let's do that. That means minus sigma 3. And if we then add those up, I'm going to have a minus 400, I have a plus 800, I'm going to have a minus 600 psi. So if I add those up, I'm going to get negative 200 psi in. So that's a compressive load because it's negative. All right. And what I'd like you to do is do the same thing for the other two corners. So if you would, just pause this a moment and see if you can make sense of what kind of signs you'll get for the other two corners for B and C. Okay, let's see how you did. Sigma C, like I mentioned earlier, it's always, all four corners have a negative sigma 1 because they're all in compression there. Let's take a look at what we'll get for sigma 2 for point C. Point C, if we look over here, it's on the side over here where we have compressive flexural stress, so that's going to be a minus sigma 2. And let's look at what we'll get from sigma 3 for point C. I'm over here on the side of the member where I have a compressive sigma 3, so that's also going to be a minus sigma 3. So let's put that down for minus 400, minus 800, and minus 600 psi. So that's going to give us minus 1800 psi. And again, because that's negative, we're in compression. And the last one then is sigma D. Sigma D also has compressive sigma 1. We'll go take a look at sigma 2. D is over here on the compressive side. D is over here on the compressive side of sigma 2. So that's going to be a compressive sigma 2. Whoops. And then take a look at what sigma 3 gives us. Point D is here on the tensile side of sigma 3. So we'll go over there, that's going to be a plus sigma 3. So let's add those up. I'm going to have a minus 400, I'm going to have a minus 800, and I'm going to have a plus 600 psi. So that's going to give me a minus 600 psi. And again, because that's negative, we're in compression. All right, so this problem really is about figuring out what exactly the load contributions are, but then really keeping track of who's in tension, who's in compression, and adding them up correctly. So If you have any questions about how this works, please let me know. And we'll move on to the next, you then move on after this video to the next one where we'll do another combined loading example. Thanks.